Everybody to, I don't remember what day, is it day 10, I think. So we successfully integrated what is basically a tiny IK solver into the leg component last episode. Didn't get as far as I wanted to, so this is that's why I added a stream to the calendar. I wanted to catch up to the other things I wanted to do. And what we are going to be doing today is do the upvectoring, which I told people, if you want to do something at home before I do it, homework pre-next class kind of thing, add that. So pretty much everybody who bothered or who asked me basically ended up doing the double cross product trick, which is, a fairly common way to do it. So if you if you don't understand this, all you need to do is to catch up to the matrix math lessons, vector math lessons from the pilot season. But the trick, which is not really a trick, basically consists of you have this vector and you would have another vector, which is, your up vector. And if you cross product twice, you will get a full transform basically. And we can do it super quick. Sketched out, where if you have two vectors like that on some plane, what people were doing is they cross these two like that and they will get one vector that's orthogonal to both. Then they will cross again over that and they will get another vector that's orthogonal to both. And so something like that basically gives you full orthonormal transform if you had the vectors normalized. And that basically becomes your full transform. Now there's, it's not a bad way to go about it at all, and it's something that you can do in a lot of situations. But what we're going to do is slightly different. Like again, in the pilot season, I was saying very often, if you know what trigonometric operations are actually going on in matrix and vector ops when you run them, usually you can shave when all you intend to do is get a single rotation. Like maybe you don't need to do you don't need to compose a full matrix, a full 4x4 or a full 3x3. If all you care about is the rotation, but Maya doesn't have 3x3. Maybe you can get away with less. Maybe you can reduce the stuff you need so that you only get the angle, and that's what we're going to try to do today. And in fact, if you did this double cross operation and you reduced it enough, you will probably find something that numerically is very, very close to what we're about to do. The other thing is that, yes, last season at the very end escalated in callbacks, and we're probably going to do the same in this one. But the idea is we always start with absolute vanilla, and we, at least at the beginning, as little scripting as possible. I mean, right now all we have is one expression and the rest is just vanilla nodes. So let's go. First thing that we want is obviously enough to get ourselves an up vector. I could have done that off stream, to be honest, but I'm sure you guys will forgive me. Now, the up vector is unlikely to get used anywhere other than in the leg itself. So I don't need to front load it in the global and then have to go through input and output and stuff like that at all. All we need to use it in, really, as far as context goes, is the leg component here, the leg IK alone, in fact. And we'll see if we want to turn this leg component into leg IK and do the leg FK into a separate one, and then have a post-flight component that basically blends the two or something like that. Or if that scatters the controls and the names too much, we might just do the leg global as a front load and then do IK and FK in there. It also depends on how granular you want the ability to update things. So the more you split, the easier it is to update subsets, but the more painful it is to do large updates that span more components. With all that talk out of the way, so for an upvector, all you care about is the position. So you really don't need to, come on, I can do it. You don't really need any particular icons, any particularly meaningful icons. This actually does, oh man, I hate that, but whatever. Let's get rid of that. So to do the right thing, you know, you can't really do with NURBS, you can't really do sharp angle square. You need 4 subsections, 4 discontinuous subsections. So Maya does that to stay correct, but it gets you 4 shapes. Anyway, and we are gonna say this is Lego IK upVector. This is gonna be our control, and maybe we don't show shapes. Oh, actually this is, yeah, so this is 4 full objects under that one. We'll replace it eventually. It doesn't really matter that much. We just have to, you know, we name things sensibly and we know what we're gonna do and where. We want to probably buffer it so that we can place it somewhere that makes sense to us and keep that transform at 0. This will be the equivalent of using pivots. Up to you whether you want to complicate your life by dealing with pivots as an attribute or as a DAG item. So, all right. Now the first thing we want to do for upvectoring is basically find out how much do we need to roll around these axes. So let's bring that up again. So we do have an axis, and at this point, like the IK handles like show you this, and this is you could call it a tensor, you could call it the IK tension. It doesn't really matter a whole lot. It's a fairly intuitive concept. Now, if you take an axis, there is a type of there is a way of defining rotation, which is axis and angle, which is one of the outputs that you can find from angle between, where you go, okay, there's an axis here. That gives you general direction, and from that you could solve maybe 2 angles in an Euler system where you have, you know, x, y, z as rotational effort, but you could not get the third. You can't get a full system where you have the roll as well. You couldn't drive a plane from that. So it adds a 4th parameter, which is the angle. So you pick an axis that gives you 2, which is your general direction, and then how much you roll around that. It's actually pretty useful, and it's good that the angle between node does that. I'm sure we'll find a use for it at some point. Now, this also happens to give us a plane. And so let's do perspective drawing. Oh man, this is gonna be hard. Drawing in the same perspective as Maya. So this also gives us a plane, and that's, sorry, that's our Y plane, that's incorrect. Oh, this is gonna be exceedingly hard. Anyway, I'm sure you'll get the idea. And this is the plane that we want to roll about. Now, what we want is this upvector to give us something on that plane. Because if we have that plane and we have this axis, which we do, we will get it. Raf gets cookie for... Yeah, I've decided to start trying to be correct about it. Sorry, somebody in chat was saying Raf gets a cookie for correctly pronouncing Euler. When I say Euler at work, just about half the animators look at me funny. So I had to regress to a more primitive form of Eulering. Anyway, so what we want to do is, right now, this upvector, let's get another color. This upvector will get us this position, which isn't terribly useful for us, like the angle coming out of that doesn't really represent a lot. But let's say that our projection is going to be in blue. If we projected that on this plane, the extension of this square is still the same plane, we could get a vector like that. Now, if instead of the positive x that we're used to think of, we will get the, sorry, this for us will be the positive local y, we get the, what color are we using there? Let's go for these. We get that, then if you have the right rotation order, if you have the right chain of consequences, what actually happens is that this angle is literally all you need. And we know how to do an angle between vectors. It's pretty easy. We've done it before. You know, you can dot vectors and do an arc cosine. And projection is also something that we discussed in the pilot season, which is again pretty easy. So let's give that a shot. So if I projected this vector and this one, I will get something going down this way. I don't want it. So if you project on a plane, it's the same as taking the rejection of that. So if you were to do this, And I'm mentioning this for completeness. We're going to use a much more primitive technique. But again, this was in the pilot. So if I do this projection and then I subtract it to the rejection of those, is actually going to be... sorry, what am I doing here? The rejection of those is going to be this one, which is the one we're interested in. But at the same time, if you have full transforms, and we do because we have this thing here, you can simply suppress a coordinate and you will get a projection on that plane. So, and that is what we're going to do. This is a lot more talking than I wanted to do. That's always the case. I need to learn to do better and get to stuff quicker. Now, we do have this control. What we could do is we have a buffer, which is what we're interested in. I thought I said no shapes. Why are you doing... Oh, these are transforms, actually. So we do have this control. We do have our... We got ourselves... this was what... Yeah, this was temporarily called aim buffer before. I have taken the liberty of renaming it. I've renamed a couple nodes, like literally 5 minutes before the stream, just to... for the sake of clarity. So we want to project these onto the this y vector, basically. So if we parented this control to that, we will get it in the local space, and then we could just squash the y in local space and we'll get a projection. Now we don't want it literally parented in the DAG because we actually want to be able to move it separately. We don't want it to be driven by the buffer. So we are going to do what we've done a million times, I believe, and actually use a matrix. So if we take, again, this is pilot season stuff, if we take the word matrix of that and multiply it by the inverse word of that, we should get the local positioning of it. So all we need is a matrix mode. Remember, if you don't see these nodes, it means that you need to activate the plugin in the preferences. That happened to me probably in the first or second episode. So chat, I am trusting you as the people. Oh, I should not even try this with a Wacom. Why do I bother? Okay. I trust you, chat, to let me know when this stuff does or doesn't make sense. And we said that we want to take, and remember that matrix multiplication is non-commutative, so you have to get the right ordering. It's hard to do these. Like normally in my head I can do this stuff in a second, but it's kind of tougher to do when you have to talk about it. So okay, you have to collapse and re-expand. No, probably collapse and re-expand the whole node to get all the inputs. That's been there in the node editor since day one. So if we take that and do word inverse, what we're doing is basically the word inverse is the word transform of these is what is moving it there. The word inverse is kind of undoing that transform. So if they take the word of this by the word inverse of that, we should get a local vector. We should get the equivalent of these, the local transform of this being parented under that. Let's get ourselves super quickly diagnostic, because if I take this too far and it goes wrong, then it's gonna take me 5.5 years to debug. So okay, to connect that, we want decompose matrix, which is what gets us from a matrix to the normal SRT. We only really care about the position, so I'm not gonna bother with anything else. It always does my head in that this is called the matrix sum. Come on. And it doesn't have other options, does it? Yeah. So if we have any mathematicians, I'd like to know how these make sense, because there might be some obscure case for it. So, are we even doing the right thing, and am I using the right stuff? Let's see output. Yes. So this is clearly not doing what I want it to do, because I'm taking... I'm multiplying the vector by the buffer, so yeah, that wouldn't get me anything useful. I appear to be an idiot, so I'm using the buffer of the upVector itself. I wanted to use the IK buffer. See, point in case, debug as early as you possibly can, especially if you're trying to talk over what you're doing. These we don't really care about. So my expectation will be that we do get something out of it. And is these, yes, this is getting the word matrix. I am moving the shapes, am I not? Or something stupid like that. Yeah, I've selected. See, this is one of the reasons why I am not fond of this approach. Oh yes, no multi-edit, because this is my only the channel box can multi-edit. I need to make those unselectable, and we need to replace it. You connected, yeah, somebody was talking to me about the mistake I made. So let's try again. All right. So is these the behavior I would expect? Probably not, because that. So am I doing the right thing in first place? Is it? Oh, is it just a coincidence? No, I'm moving the buffer, so yeah, I remain an idiot. So it's not quite again what I wanted to do. I can do it eventually, it will work. So this is still not what I would want. And then moving the shapes, make it a drinking game. Yeah, no. So we have the buffer, we have the control. Am I doing something stupid here? We have the leg IK buffer. Let's see. Is these in the right place? Yes. Am I getting the word matrix? Yes. The locator parented to the word where it should be parented to, I think. The IK buffer, whatever you use for the inverse matrix. Parent inverse matrix, that's the mistake. I want word inverse matrix. So I don't know if that's what you were saying, but yeah. Why did that, man? I need to pay more attention. So word inverse matrix is what we want. All right. There you go. This was obviously all intentional to show people how to debug. Let's not select the shapes again. I'll need to make them unselectable. It was a very poor choice. So what you can see here, like this item respective, in respect to the word space, and you know, this is the Maya purple. So as soon as I deselect it, might go pretty hard to see for you guys. But now, when I move these, you can sort of see that it's representing the transform position of these as if it was a child of that. Now, if I also take that, what did I win? Oh, someone was actually telling me you connected the parent inverse matrix of the buffer, and I thought they were talking about a previous mistake when I was hooking these up. I don't do no prizes for these, but I wish I listened. So if I do that, and I do not deal with the X, with the Y, I'm basically suppressing the vertical part of that projection, assuming, and let's say that our word plane is actually this plane, and it is in this case basically, that I want to work on, assuming that our buffer here is Y up, yep. Now I basically have the plane projection that I was looking for. If that makes sense. I hope it makes sense, but basically I'm projecting this thing on the plane of my IK tension. So, okay, that's not too bad. Like, it's what we wanted to do. I mean, it just took me 15 minutes longer than I wanted to. Well, maybe not quite that bad, but. So, we do have that. Need more coffee, man. It's I've had probably too much coffee already for having been awake for like almost 2 hours now. Anyway. So we don't care about this. This is just a diagnostic. What we actually wanted out of it is a vector. Now, we do have our vector, and we are actually interested in this thing coming out. Since we projected this in this space, this going out that way, if you think about it for a moment, is actually pretty trivial. This is just our z vector when you compare that to that. So we can use an angle between, and we don't need to parent anything in this buffer so on, because we've transformed that one, which means that unless I have some other mistake in there, which might or might not be, we'll see. All I need is to do, and we probably want minus z, let's not repeat the mistake that we made before, to get the minimal angle. We should be able to get that, where did I put it? First slot, second slot. Now these angles should suddenly be fairly relevant. So again, let's cut these out. And let's do that. And let's see what we get. I would expect these to now, we can actually move it somewhere else. And I should use more of these objects really, but whatever. Bear with me. We should now be able to connect the rotate of these, and now it's giving us well, I definitely need to change that control, it's silly. So this is giving us more of an angle than I would have expected, like more of a direction than I would have expected, because I would have expected these to be flat, to be honest. So what's the output of these? Do we have shenanigans going on anywhere? Unless the angle between is trying to do more than it should be doing, but I don't think so. We might want to make it y dominant, but angle between doesn't take a rotation order, so that might be unwise. I'll select the NURBS all the time, because the problem is that that's what you select. That's why I'm not fond of this multi-transform approach. If I can't do otherwise unless I do it from the outliner, so I don't think it's a fair drinking game. So it seems to be mostly right. What I will not want is for this to happen. So maybe, oh, I know what I'm doing. I did not, because I connected the translate right away, and I did not suppress the y the way we said we would have had. That was the problem. So the other thing we want to do is here this one. Yeah, it's the stream is on spot today. Every time I turn around to look at the chat, somebody is telling me to do what I've basically been doing. But other than those mishaps, there you go. So that is literally all you need to do. You project by simply parenting with a couple nodes. You suppress the y. That's the equivalent of a projection, because we're in a very controlled environment here. And then you get an angle between. Now, if you wanted, you could actually add these very trivially to your solver back here. Because when you look at the actual dependencies of these things, this does not depend on that buffer. Sorry, this does not affect that buffer, which means anything that comes out of there through some other operations could easily go in there. And this angle between is literally just a dot between a couple vectors and an RCOS. Now, we're not going to do that because we want to avoid making that expression ginormous, but we could now try and plug that into SRT. So the rotation order matters a whole lot here, like a lot. Luckily, because this is the IK part, animators don't need to control these, so we can be pretty liberal. So, and somebody's asking, is it cheaper performance-wise to multiply two transform matrices than to do the double cross product? It depends. If you start having 4 or 5 nodes to do something like this is probably cheaper. But what I refer to in terms of like why I would look at a method like this is, if I was to write this solver in full, which maybe we will later. I mean, you see how small that expression is. You need to add very little to make it into full IK without vectoring. Then yes, like this kind of operation, I wouldn't use the full matrix multiplication. I will reduce this to practically nothing, because this is literally just a couple positions and one rotation that I need. So that will compress a lot. And because we don't care about the Y, in fact, if you really wanted to optimize piecewise, you could suppress it even more. These will come out to a lot less actual scalar operations than doing a double cross product, and cheaper ones at that. If you're doing it with nodes, you have to consider your node tax, like how many nodes do you need. If you're doing it with expressions, you have to see how often that expression is going to store your evaluation and so on. Hopefully that answers it. Now, the other thing that we like about this is that it should give us just the one axis as a result, the rotation around the one axis, which is very good. So from that buffer, now you have that crap selected, from that buffer, now we were already controlling the rotation for these piecewise, like one bit at a time. We probably don't need these. Let's keep that locator around just for the sake of having a diagnostic at hand. So this SRT with this rotation order basically means that when the X rotates, it will take the Y with it. And this is in gimbal. So you can see that all I'm doing through the buffer and setting the X rotation is basically making my Y always reliable for a roll. So if I do that, I always get a roll that does not move these away from my IK handle. Enough talking, moment of truth. I think this was being set on the Y, which makes sense. And we will want that in the Y as well, yes, I believe. And then we might need to tweak by what angle we pick up from where and so on. Yes, I'm selecting the curves. I have to remember to do that. So let's start at some default position. Yeah, that seems reasonable. It seems like reasonable behavior for an upVector. We will need to play with these a little bit more, maybe, to make sure that we look at all the corner cases and all that crap. Doesn't count for a drink because you recognize it right away. Okay, so we do have some technicalities to these. Yeah, all right. It's yet again, this might feel anticlimactic, but I think any solution that is good because it's simple will inevitably end up being anticlimactic, because you tend to work a reduced number of items. So you get one value out and you're like, yeah, I'm good. So there might be issues with it. Like, no, actually, that's the pretty good expected behavior. Now, I was about to say, due to the little bit of magic that we're finding the angle between is doing for us, it might have behaved in a more solid fashion than expected, but no, seems to be good. What is the chat thing? I mean, it's really that simple. I hope like this isn't really about the IK per se. I mean, sure, it's useful to know how to do one, but it's about the inherent simplicity of doing these things. If you think just a little bit about what you're doing and you try to reduce the transforms, it's simple enough that you can do it with nodes that are not meant to do these things and expressions. And if I was to write my own solver, so this will be probably 3 or 4 lines of code. The expression that was in here, which is mostly set in variables, is like 2 lines. Yeah, the node to do the entire IK is likely to be like 60, 70 lines of Maya CRUD for the plugin and the parameters and the M status and all that. and the evaluation is likely to be dozen lines or less if you're pretty verbose. Now, what do we have? We have another 20. I hope that was a lot. We have like another 20 minutes. Now we should solve. Sorry, we should save. We have already solved. I'll rename these off stream. We don't need these. 67 lines of boilerplate on the instinct. Now I think you're looking at that for a single node, a single plugin, unless you're going all documentation style, everything has to catch the AMP status. I reckon 60, 70 actual lines, not including empty lines to space your code out. Anyway, but it's, you know, it's fair enough. It's a plugin system. I've seen very few plugin systems that are very concise and very synthetic, and when they are, it's in C++ at least. When they are, it's often through macros and stuff like that, which, you know, might be good, might not be good. Anyway, so I should probably either add a upVector to these or delete it, but we'll do it later. Now we have 20 minutes, so what is a good use of this time? Maybe a little bit of math. Making this guidable, maybe we'll do it later, like in a later episode, maybe tomorrow. Now there's a classic problem that everybody's aware of, and bear in mind, like if you manipulate really slow, you know, you might get some slight discrepancies. So you don't use checkman? Yeah, no, I don't use this stuff. It's so rare that it's of any use. Sorry, somebody in chat was asking if I use checkam status and return it in place of a semicolon. It's a Maya macro C++ thing for plugins. It's just, I find it ridiculous. Like normally if you get a failure, like a hard failure, you get a hard crash anyway. I find that crud. Some people like it. So the other thing to keep in mind is that, and we'll have to look at it, you might see some red flashing in there. There is a case where these Arcos, yeah, there you go. This Arcos is basically getting a value you can deal with. We don't really care about it just yet. It's a benign error for now, so we'll solve it later. Now the pop is, you know, the classic IK thing. Where does that come from? Let's keep this a short stream, but let's also do that. So when you go down with the IK, you know, there's time when you're getting to the limit of the IK where and hopefully you can see it, the stream is high frame rate enough for you to see it, where you're moving a pixel and that happens. And you'll see that the expression is suffering less for it, but it's just suffering for it later. So you get an even bigger jump. And that might be precision, that might be anything. It's not really the point right now. And you'll find all kind of crazy systems to go like, hey, we're doing soft IK with auto stretch and, you know, control lag and all of that. And we'll get into soft IK. I think the way, like, the laggy soft IK is a terrible idea. Now, the simplest thing to prevent that is to lock the solution of the chain. And I mean, that might seem like an obviety, but why is it? Oh, because it's an IK thingy, so it's doing some silliness with the joint orient. Anyway, it doesn't matter. I see that's why I don't often use joints, because I'm pretty positive I had zeroed these out eventually somewhere, and still now they have joint orients all over the place. Anyway, so if you limit, if you dampen or limit the rotation, you might get, you know, different behavior down there. You might make it less prominent, or you can just hard lock. And right now I forget where it even is, to be honest. Stiffness, prevent. Is it just the normal transform? Possibly. So transform attributes, join labeling, limit damping. All right, never mind. So let's use a hard limit for these. Now, if I limit these, and the silly joint orient makes these things so much worse. I don't want these. Maya, don't do this to me. Okay. And it might have changed. Yeah. Yeah, that's another reason why I don't like the solver. If I limited the rotation here so that you can't extend past that, then I will basically be good. And I'll explain why. You will not see that pop. And that might seem like an obvious and possibly even bad solution, but the reality of things is that if you're doing something that is deforming, so if I limit that to that kind of configuration, and let me actually deselect it so it's a more visible color. My daughter is saying hello. Possibly, we don't know what she's saying just yet. And if that is the default position, and if you have your mesh set up straight, which I hope you don't, but some people receive modules like that. If that is your default, because everything is offset a certain way and you're well inside your parameters, then your actual mesh will straighten just fine, and you will not get that pop because you're stopping much sooner than when things go bad. And that is a perfectly viable solution for the record. Now, if you have a mechanical item and you're rigging something mechanical, that might not be ideal because you might want the mechanical item to get perfectly straight. And by the way forces over a hinge work, it would actually, in reality, you will get that pop a lot. If you have a linear force pulling apart, by the moment that thing is approaching being co-aligned, the efficiency of the forces applied is so high compared to when it's there that you will get that pop anyway. But beside that, it might not be ideal to lock it that way. And in that case, stretching the joints, unless you have a mechanical system that has some give, is also not going to save you. That is to say, there's basically not always a solution. Now, why is that? And this is where you need to understand, I guess, the math of what you're doing. I hope that I have something saved. And I also imagine that everybody is now hearing my daughter playing. So I'd like to point out that's my daughter. And I do have something saved for the sake of expediency. So this is the formula that we have used to calculate RAK, and this is where something like Desmos, actually I can add sliders like that. And what is happening in here is my length were like maybe 4 and 5 or something like that, and I also use these as an example of why you should stay away from 0 or really perfect numbers, or equal numbers when a system has more than one term. So what is happening with that is that as you start extending, come on, this is my Wacom might just have messed with my system very badly. We'll see how this goes. At least I'm in the right app. As you basically extend, this is the progression of the angle. So you can see that it starts very linear, which is pretty good. It means that as you extend it, the response of the angle, the change, the rate of change, the derivative, whatever you want to call it, is going to be very, very uniform. The derivative is probably very close to 0 here. But when you start getting to the end of your extension, then it starts moving a lot faster. You can see that this becomes a much sharper increase, and that is basically what's causing the pop. When you're getting towards the very end of that progression, you're almost vertical, so a very minimal change in one direction will create a huge change in the other. Now, this curve, or some equivalent depending on what you solve, is also your only ideal configuration. If you deviate from this curve by introducing something else to reach your end, your effector, which is what a lot of soft IK does, it dampens this curve by making it, the further you get here, the more it dampens it, so you get more of that kind of feeling. It means that the further you go down these, the further away from the ideal solution where your effector and your control are in the same place you are going to be. So that's why it's very far from ideal, because you will never have your IK effector where you want it to be. Now you could think that tweaking this a little bit to be in an ideal position, it will be simple, but here's the thing. And I hope this part makes sense. I know it's very mathy. The vacuum is completely whacked, but the mouse seems to work, so that's good enough. What is important to understand here, and by the way, if I'm doing this, it's also because there's some cool stuff that we're gonna do with showing the actual Cartesian mapping of a function and my itself. Now, the fact that it goes like that, there's a lot of meanings to all these things. It means it's cyclic, so you know, if you were to move the other way around, because these are all square, they're all unsigned, they all get, you know, automatically, regardless of whether you're negative or positive, they always get positive eyes. It's cyclic. There's all kind of properties that come with it, but the part that you're interested in is this stuff, like the way the curve changes here and here. Now, these are the length of my two bones. So if you were thinking, okay, I'm gonna write some approximation of this curve, you are in terrible luck, because what happens is that as you change the length of the two bones, the actual shape of the curve changes a lot. And it is sort of like, it starts changing very little at one point. It feels like it's mostly scaling. So for very dissimilar length of bones, you can actually generalize. But then the moment you actually have bones that are the same length, which is what we had here, you can see that it goes very, very sharp. So if in this case you had that kind of like strong change with very little movement, when your bones are different lengths, you will see it here as well, and a little bit less of it here. Hopefully that makes sense. Now, the reason why you don't observe it a lot in the rigs is that very rarely that sharp change I was talking about, if I make these two, ooh, danger, you know, if I make these two different lengths and all of that, you will notice that, because that function is already distance, you will notice that only, and we limited that, only when the control and the hip are very close, extremely close, and people just don't get in that kind of configuration unless they're, you know, trying for some ridiculous exaggeration or it's very special rigs or whatever. But people are at the full extension all the time. Now, when you limit the rotation to stop at a certain point, you basically prevent the sampling of this part where the function is really harsh and unfriendly. So this part we cannot care, this, you know, this part, and we'll look at approximating this some way, and this part we want to avoid. So the moment you have it, and what were we using, 5 and 5? I suspect so. So 5 for that, and 5 for that. So if we go back to those numbers, and next episode, as we get to guides, you know, we'll talk more about this, and you look at the function itself, like this is where you're starting to go, okay, this is really poor. This is really poor behavior. But probably up to here, like we could, you know, run the derivative and see where we get something nasty. But you're at 9.8, so we're not talking about a huge limit. We're saying that if we stop these from, you know, going past 9.8 distance from my maximum is actually gonna be 10. You are talking 98 out of 100. You're talking 98% extension. Does that make sense? I hope it does, because for when we'll get to numerical methods and stuff like that, hopefully it will make more sense. But it just, you know, we got the upVector done. I just wanted to start introducing what we're going to look at for the pops and stuff like that. So right away, armed with that knowledge, someone is asking, would you need to adjust the limited ankle length to account for the fact that you're not allowing the chain to reach its full extension? Yes, that is kind of, that is actually what I was getting to. So if I want to lock it, now I could lock the angles here. one way or another. But an even easier way, because of the way I graph this, because of the way I think of my solver and all of that, because of the way I have very real, very good numbers. I mean, even at 9.923, so you're looking at 99.2%, coverage. You're still doing yourself a huge favor. And because we worked in that way, what we can do is literally just limit how far you go, and you're done. That's the axis of your function that you have the most immediate control over. So now I have to find where that is. It will be somewhere here in the limited ankle, hip to ankle, ankle clamp displacement. So this is limiting itself. This is, where is it? Clamp displacement. There's a really odd noise. Cos'è sto rumore? Oh. Sorry, from the mic. There was I'm sure you guys are hearing these as well. Actually, I think they're using a water lens outside to clean some wall or something like that. Anyway, so what we want is to find the single value. So this is the multiply. What am I looking at here? Because this is now confusing me officially. So this is the direction, this is the distance, and this is the part where we're clamping. So for a moment, let's say, so the max should be connected, but I'm not showing where. Let me pin all of these just in case. And let me save as well. So the max should show a connection to something, which we might need to rename maybe. No, we're good. Now if for a second we forgot about that, or we multiplied it by 98% to choose, how much we want to limit. Actually, let's do that. So is there a mode that is mode double linear? No, the multiply divide. Why am I forgetting this stuff? Because there's add double linear, mode double linear. Why was it not coming up when I type mode? Whatever. So if I actually took these and plugged it into the max, maybe in a better way, let's not make the usual mistake, and say this, hey, your limit is actually, so that's 10 multiplied by 98%, so 0.98, then, that, like, it's reducing the angle a lot. Like, that's the kind of thing we're looking at. I suspect this is actually over limiting. This is not. There might be some other factor coming out of these, but so we're seeing a very harsh change at 992. So yeah, that's the kind of numbers you're looking at, and that hopefully will give you an idea of how much angle comes from so much distance. Now the distance is the most important thing, because it's the one that makes you reach the point that you want to reach in animation. So if you have anything that is soft deforming, this is the least damaging limitation you can introduce. And then the fact that you're skinning to differences anyway will take care of hiding the fact that your angle isn't fully extending. If you're dealing with mechanical, it's a trickier thing to do. But realistic mechanical systems rarely get to fully extended without actually wanting a pop in there. So we are in time for this, and hopefully all of these make sense. If we have any questions, please put them in now. And let's name these as well, just in case. And for the record, what, you know, some form of stretchy IK basically deals with when you go, okay, I'm gonna stretch the bones. It's not really, you know, soft IK. I wouldn't say that's soft IK in a way. That's an adjusting system, but this knowledge is pretty important when you want to do something like that as well, because your understanding of this part of the function, if we find a good approximation for the first part, your understanding of this part of the function and how you can smooth it out by, you know, yes, scaling the joints to reach the length, but at the same time rotating them in a little bit so that you get closer and closer to that collinearity is pretty important. And when you look at this, it might seem scary, but because, you know, graphs and numbers and formulas, it's actually pretty easy. You know, I imagine for a lot of people, from what I heard, doing stuff like, you know, matrix mode and an angle between was very scary before the pilot season, and now, you know, people don't think twice about it. Do you usually use a soft clamp of sorts to clamp the distance, or just a hard limit like you've done here? So you would have to explain what you mean with soft clamp. I think I know what you mean. But the soft clamp, if I understand what you're saying, is basically what would introduce latency. So if I clamp hard, and most of the time I would do just that, to answer the question, you know, quickly. Most of the time I would just find, because you're talking animation, you're talking deforming things, there's so much transformation of that signal and so much noise going in that you don't really care for full respect of the function. If you consider this a functional space, and if you have uneven lengths, I know that by the way people work, because they don't ever, like, there's no real point to having the hip and the ankle like being exactly in the same place. I know this part of the function is of no interest, and, you know, because we'll limit early, you know, we're ignoring it. That's what you're doing when you're saying, you know, the two things, like let's be at a minimum, and we've done it in this read. Let's be at a minimum at 1 apart. You know, you've ignored like this chunk here. By the way, if you see the function moving, it's because the leg parts are now of uneven length. So what is happening? What this number that you see here is when the two joints, if they were to align like that, so when your angle is 0, this is the distance between the two. So if you were to ever approximate these, if you do, you know, 5 minus 3/7, you will get this number. Whereas this peak remains the sum of the two. Doesn't leg getting longer emphasize the fact that the joints aren't actually straight? No, not really. So the question is, when you add stretch AK to a system like this, doesn't the leg getting longer emphasize the fact that the joints aren't actually straight? You might get, and it's, you know, might be a much longer explanation. What you might get is basically a change in, like, mathematically speaking, you might get a change in second order derivative. So something that should have been, what you could get is that something that should have been perfectly straight, as you do all of your compensation, and it was going from this to that, it might look very slightly like that. But that's why I was saying, if you think of this as treating signal, between the fact that you have points which have been kind of hammered, crudely hammered to the joint transforms, you know, when you're doing your weight painting and stuff like that, you're not really following any numerical methods, or even if you're binding to an actual spline space, you're not really doing things very precisely. The animation for anything that is good looking is normally very organic, very messy, very noisy, let alone if you get anything from the real world, like with mock-up, there are so many forces like hammering anything that moves that you always get a lot of noise. That's what real world movement looks like. By the time you've pushed your signal, so you're literally two angles through all of that, it's a not, if you take a shortcut, if you suppress a part of the function or you do something like that, it's practically unnoticeable. The signal coming out is so noisy and scattered. So no, if you overdo it, yes. The main thing with these is making sure that it doesn't ruin the animator's experience, which is what laggy soft IK does. So let's super quickly discuss that. What some people do is, you know, they decide, and maybe they know it, maybe they don't. Maybe they know that they're treating a function, or maybe they just find magic numbers and do it in, you know, on some instinctive level, instinctual thing. And they go, oh, when I'm here, I'm gonna start multiplying these by the square of something so that this curve starts tapering out, and you know, they're changing that curvature from going in this direction. They're adding a function in that goes in that direction, so with a different second order derivative, if you want, or the different third function, whatever you want to call it, so that this straightens out. And the closer you get here, the harder these things push it away. And what happens is that you get lag. So when your IK is here, you know, you're in the safe space of the function, you're good, and your control is here. When suddenly your control is here, and this is very close to the pop, by changing the nature of that function, what they're doing is literally introducing latency. So this is now starting to be, you know, your friendly function here, there's a gap to your real function, the one that gives you the correct values. It manifests itself in the IK here, the effector of your IK being distant from the control. And when you're at full extension, like, you need to extend a lot, like a lot, to get to something that might be very close to your terminus, and you might even never get to the terminus of that. And the rationale of that is that, hey, this way you can animate your control linearly, and you can expect a linear response out of the angle. So your angular effort is fairly, you know, is fairly well behaved. You don't get that sharp jumping angle when you have a small linear displacement change. I think it's a terrible idea, because it's really nasty. Like, if you think of games, if you think of UIs and all of that, when you're moving something and you have latency, and we're talking like, you know, milliseconds are already perceivable. It is so nasty when something lags. It's such a terrible user experience, and introducing that as a solution to anything, like, strikes me as, you know, very misguided. But even without that, when this thing moves, because you have introduced this function that is divergent, the animator especially if they're extended, the animator fully expects that your control, and their idea of the control is they're moving these. This is just a manipulation thing. They're moving these. That's going to be exactly on that line, especially if you have a path. And what happens is that depending on how extended you are always going to be a little bit far away from that, and that how far away you are is very dependent on the extension of these. And if you're, and this, you know, the argument for this is like, oh, but this is really useful when you're, you know, your control is a million miles away from your leg. And you go like, I don't know of a lot of animators that have a character that is up in the air, off the ground, want the leg fully, like 100% extended, and they will use the IK by placing the control a million miles away, when then at the landing time they will have a function curve that jumps a million miles. Yeah, I don't think soft IK done by lagging your function, your evaluation function, far off your actual ideal angle to distance function is a good idea. I think it's a terrible idea. And stretching can help it, because you know, your aim here is to reach this point, and if it means that you have to stretch these bones a little bit, you know, you lock early and you want your numbers to be correct, then you stretch a little bit. What the stretching will do in many ways is kind of like reducing your perception of that angle anyway. And if you couple that stretching with more of that angle change, you know, and it's magic numbers, you have to finally tune it, that you can get very, very, very close to straight with something that has a good feeling in that stretching. And stretching, you almost always want stretching in the IK anyway, because it's just the feeling of it. It's, you know, in reality, when you pull a leg like that, if you got to the real extension, your femur can come a long way off its hip seating before there's real damage. So that is a good feeling for a rig, and it's also not incorrect. So, okay, I reckon that was more than people bargained for. I was under the impression that people use that latency function only in a certain radius of the stretch, and beyond that it reverts to the normal behavior. It's possible. I haven't seen it like that, but I'm sure somebody does it like that. It seems even more misguided to me, to be honest, because at that point your function for these to be aligned with the control, which is the expectation that the animator has, will start looking something like these, possibly, instead of being, you know, this is the intended function. And then you go like, okay, and people do it with magic numbers. They very rarely go and find, you know, an actual polynomial that properly approximates what they want to do. So you'll find the kind of, oh, if from here to here they multiply by these magic numbers, so it kind of straightens, and then you start getting these discontinuities. And say it is such a simple problem in essence, which is like, it's almost impossible. It is impossible to be perfectly aligned and have the right angles. You can't have your cake and eat it too, basically. The most reasonable thing to do is limit out the harshest part of the domain, and that will get you a very long way. If you have mechanical, that's a different thing, because that's tough. That's really tough, because in mechanical, you know, the lag is just lagging the control. At the point you could tell the animator, hey, it's, you know, be careful about your function curve, or give them a tool that when they're reaching that extreme will actually smooth out their function curves. Yeah, the softness thing is often just a factor of sort that comes in and linearizes these. But then, as you say, at some point, some people might want to return back to that to get, I don't know what. It's just, it doesn't make sense to me. It doesn't mean it's, you know, it's bad. I don't think it's good. I wouldn't use it. I don't like it, but it works for a lot of people. If your animators like it, do it. Anyway, all right. I'm going to conclude with that. Nah, it's all right. I'm still going to make it work on time, but I got to dash. All right. Thanks, everybody, for watching, especially the people on the stream. You guys are the best. But even you guys on YouTube, you're still right. Thanks for watching too. All right, have a good day, everybody.